In this lesson, we're going to be talking about two sample inferences for means. We'll use mu and mu1 and mu2 as our parameter notations. This is going to be covered in sections 10.2 and 11.2 of your textbook if you use the Practice of Statistics updated 6th edition. If you are just looking at this video from randomly searching and you find this helpful and you don't use this textbook, make sure that you find what part of your textbook this follows along with. Let's get started. With quantitative data, we're going to be specifically talking about two independent random samples. We're not talking about paired data here, so these got to be independent. So when we're dealing with independent samples, we're either going to do a t-interval, a two-sample t-interval for the difference in the two means when you're trying to estimate with confidence, or you're going to do a two-sample t-test for the difference in the means when you're trying to test a claim. And you'll know that by the wording of the question. So there's two formulas that you're going to be working with. The first one, the generic formula for a confidence interval, any interval is the statistic plus or minus the critical value multiplied by the standard error. In our case here, that's what it'll look like. It'll be the x bar minus x bar 1 minus x bar 2 plus or minus t star. We use t because we're dealing with means with an unknown population standard deviation. And this standard error formula you're going to find on your formula sheet. If you have your AP statistics formula sheet handy, you'll be able to see that. If not, you can Google, if you Google the AP statistics formulas, usually that first Google search there, if you type AP statistics formula sheet, will pop it up, and then you can see the updated formula sheet based on the 2020 exam. The test one is going to be the generic statistic minus parameter over standard error. And of course, that's going to look like this, the difference in the two means with 0 as your null, because we're trying to assume that there's no difference, divided by the standard error. You'll notice that's the same standard error formula. And from your formula sheet, what I had circled there in red actually would be found. Now, you'll see the generic formulas in red up here, which on the front side of your formula sheet for the test statistic and the confidence interval. And on the back side of the first page, you'll see the standard error formula for two populations for x bar 1 minus x bar 2. But let's play with some numbers. So we're just going to see if we can enter the data incorrectly and get the interval and the test statistic and p-value without adding context at the moment, because I feel like the context kind of weighs it down a little bit more. So write these numbers down. X bar 1 equals 9.3. The standard deviation of that sample is 0.85, and the sample size is 20. And for X bar 2, we have the mean of 8.8 and the standard deviation of 0.96 with a sample size of 18. So what we're going to do first is we're going to calculate the interval and the test. I want you to pause the video and see if you can identify the part in your TI-84 calculator that has the two-sample t-interval. It's going to be option 0. And the two-sample t-test is going to be option 4. And when you're calculating an interval, you're going to either put the data in L1 and L2 if you have the lists of numbers to work with. If you have the statistics like I'm giving you here, you'll go ahead and put that right into the stats. So if you highlight stats over there, it'll bring up the space to put in the X bar 1, standard deviation 1, and so forth. And then finally, set your confidence level or your alternative hypothesis, depending on if you're running an interval or a test, and never set the pooled. Now, that's kind of a more nuanced approach that you would maybe learn if you do a more advanced statistics. But with our calculator, we're gonna keep it unpooled, and for reasons that you can kind of look up on your own if you'd like to. So what we're gonna do is we're gonna pause the video and see if you can come up with these values here using your interval and your test. I'm going to go ahead and walk you through it. You're going to press the stat, test, and the first thing I'm going to do is the interval. So I'm going to go down to option 0 and do two-samp t-interval. I'm going to go to stats, and I'm going to enter in the numbers that I have over here. So I'll do 9.3, 0.85, and 20. We got 8.8, 0.96, and 18. I'm going to keep my confidence level at 95%, keep it unpooled, and go to calculate. And you should get your interval here about -0.1 to positive 1.1 with a degree of freedom of 34.21. I'll explain what that degree of freedom means in a little bit later. And you'll have all your sample statistics that was provided to you already. Again, if you go back into the menu with test for option 2 sample t test, we're going to go to option 4, excuse me. And if you've already run the interval, you'll still have that raw data, those raw stats to enter in from the test. I'm going to just do a not equals. You could, again, I don't have any context, so you could really do either one of them, but I'm going to hit not equals, go down to calculate, and get all this information. And you'll see that the degree of freedom is the exact same as for the interval. The test statistic is 1.69 and our p-value of 0.0997 with all the same statistics if you scroll down. So as you're going through that, make sure that you know how to get that information. That's basically the do part of a state plan do and conclude. Now, the degree of freedom is a very complex formula that was developed many years ago, I think in the 1940s, by some statisticians that allows for a less conservative approach. So you have basically more precise data to work with. You don't need to memorize that. So if you're using your calculator, you just report DF, but you don't have to explain where it comes from. It does have to do with the sample sizes, the standard deviations. There's a lot going on in there, obviously. Now, if you're doing this by hand, which you may see in multiple choice questions, the T-star and the test statistic worked out by hand, then they may use the more conservative approach to the degree of freedom. On a free response, I would shy away from using it, but if you're using a conservative approach, you might see that happen on a multiple choice question. So here's how it goes. If our two sample sizes, in this case 2018, we have to pick the smaller of the two to subtract our 1 from. So you know it's going to be 17 here, okay? So when we're looking at that 18 there, subtract 1 and you'll get your degree of freedom of 17. Not the 34 point whatever your calculator represented, just plain old 17, okay? Now what that does, if 17 is your degree of freedom and you're calculating an interval, you're going to go and use the formula. Then you're going to still plug in your means and standard deviations and sample sizes into that formula. Remember, the formula is not going to be outright given to you, but the standard error is. And know that we're trying to estimate the difference in the two means. And that's why we're subtracting these two sample statistics. Now that T-star, you're going to get that using, well, you can get that using your table. If you know that your degree of freedom is 17, and let's say we're using a 95% confidence level, then you can kind of match the row and the column up, and you'll see that your T-star here would be about 2.110. Again, only use that if you're going to use the formula approach. You would plug that in for T-star. You'd want to calculate the difference in the means, so you have your point estimate, which is about 0.5 in this case. And as far as that margin of error goes, you'll throw that all into your calculator like this. Why don't you pause it and see if you can get that value as well. And you get about 0.6235. So that's going to be your margin of error. And that should give you an interval between about negative 0.12 and 1.12. Now, if you recall the interval we got using our calculator, the calculator one's a little bit narrower. It's still the same confidence level, so it's still 95% confident, but the calculator is using a less conservative approach. So it's going to have a more narrower, precise interval, which is, in my opinion, a good thing. I think that you should use that when you're doing a free response question. So again, you're not necessarily going to see this 2.110 by hand and calculate the formula by hand unless maybe you see it in a multiple choice question where they're using the conservative approach. And on a free response, use the calculator. Now, as far as a test goes, and let's say this is a two-sided test for our purposes here. If you're doing the test statistic, you're going to do the difference in the two sample means minus 0 because the null is 0 divided by the standard error. That might look something like this. And of course, we're going to want to calculate that test statistic. And so we get about 1.692. All right, that's our T. Now, if you are going to use the conservative degree of freedom, then you're not going to be able to use the test menu to get that p-value. You'll have to think about this being a two-sided test, you'll have to know that that's the likelihood of it being above 1.692 on the t distribution or below negative 1.692 since it's two-sided. And so that's going to look kind of like this. You'll have this symmetric, shaded part on the right side and on the left side. And I use the TCDF. Let me show you how I do that. So on the home screen, if I go to second vars and I go down to TCDF, and in this case, since my t is a positive number, I want to go above it. If it were a negative, you'd go below it. Since t is positive, you do 1.692. And your upper, just make a really large number so we can replicate infinity. And our degree of freedom would be the conservative degree of freedom, so we'll use 17. And as you can see here, we get about 5.44%, 0.054. Now, if the t test statistic ended up being negative, so let's say all the same was, but we just subtracted it in the other way, then it would look like this. You would have your lower be negative infinity, and your upper would be the negative t test statistics, so negative 1.692. Same degree of freedom. And it's the same percentages. But since this is a two-sided test, we're trying to test to see if it's not the same as. So we basically double it. So when you're reporting a two-sided test, you double it. It's going to look like this. The area above is about 5.44%. The area below is about 5.44%. And your overall p-value, that's about 10.88%, 0.1088. Now, if you remember our p-value from before, it's not that much different. It's the same test statistic, 1.692, but the p-value from before is slightly more because it is a more conservative, or I'm sorry, the p-value that we got by hand is slightly more because it is a more conservative approach. So I would say, use your calculator again if you're using a free response question, because that's going to be a little bit more precise. It's going to have more accuracy, and not more accuracy, it'd be more precise. It would be less variable, so that p-value is going to be a little bit smaller. At the end of the day, though, we're still going to have the same result. With a p-value that large, we would probably reject the null hypothesis if we were set to 5% alpha level. So those are how you do those by hand and calculator. Now let's just go over the 4-step plan. You're going to use the same 4 steps that you would do for any test or interval. If it's an interval, obviously name it, whether it's an interval or test. Your calculator's generic name, 2-samp t interval, 2-samp t int, or 2-samp t test. That's fine to write, but it's better to write the actual test. So 2-sample t interval for mu1 minus mu2, or 2-sample t test for mu1 minus mu2. Make sure that you define your parameters. What is mu1? What is mu2? Do that in context of the problem. If it's a test, state your hypotheses. It's for the null, it's always going to be mu1 equals mu2, or that difference is 0. And for the alternative, it's either going to be not equal, greater than, or less than, depending on the problem. So read the question carefully to determine that. And finally, make sure that you state your confidence level and your alpha level, especially if they aren't given to you in the problem. Then your conditions, we're going to do our random, 10%, and approximately normal. A lot of times the textbook's going to say to name the test here. I do that at first because a lot of times the scoring guidelines are just going to look for the name of the test. So just get that out of the way first. So we're going to state our conditions, random, 10%, and approximately normal. Remember the random, we want to come out on both samples being random. Both, not just one, but both of them, and independent in context. If it's an experiment, make sure you say they're randomly assigned. If it is not an experiment, so if you're selecting from a larger population without replacement, we want to make sure that both of our samples are sampling less than 10% of the population. That condition's been there for a while, and that we want to make sure that gets mentioned if we are sampling from a larger population. And then finally, the approximately normal condition is just stating that our sampling distribution can be modeled with a normal distribution. And that's going to be the case if the population is considered normal. So if we're told the population is normal, which is very, very rare, or if our sample size is large. A lot of times our sample size being 30 or more will meet that central limit theorem, so we're good on that. Or in most cases, we'll have to probably plot the data because a lot of times with experiments and means, we just have smaller samples. So we want to plot the data, see that there's no strong skew or outliers for both sets of data, not just one. The do part, I stick with the calculator on this one. Report the interval, report the degree of freedom, report the sample statistics, especially if they were not given to you. So if you just get a list of data, L1 and L2, you don't have sample statistics to work with. You got to write those down with the correct notation. So make sure you write all that from the calculator. Report the interval, report the test statistics and p-value, report the degree of freedom. Make sure you write the sample statistics. For the conclude part, depends on an interval test, but it's the same conclusions you'd always make. For the interval, we are blank % confident that the interval between this and this captures the true difference in these means in context of the problem. So for our numbers here, we'd say we were 95% confident that the interval between negative 0.1 and 1.1 captures the true difference in these means. For a test, we either have a rejection of the null hypothesis or we fail to reject, depending on our p-value. So if our p-value is low, we're going to reject the HO. We'd have convincing evidence. If it's high, we're going to fail to reject it. We do not have convincing evidence. In the case of this problem here, the p-value 0.0997, we probably fail to reject the null because that's greater than 5%, which is what we usually use. And this was a two-sided test, so we'd say there is not convincing evidence that the true difference in these two means is not equal to 0 in context of what the problem is talking about. And that's that, guys. So we got 2 questions for check your understanding that I want you guys to try. So pause the video and see if you can work through check your understanding 1 and read through the question. I'll read it for you and I'll kind of walk you through the steps. So if you want to read it on your own, pause it right now so you can process what's going on here. All right, Mr. Wilcox's class performed an experiment to investigate whether drinking a caffeinated beverage would increase pulse rates. 20 students in the class volunteered to take part in the experiment. All of the students measured their initial pulse rates in beats per minute. Then Mr. Wilcox randomly assigned the students into 2 groups of 10. Each student in the first group drank 12 ounces of cola with caffeine. Each student in the second group drank 12 ounces of caffeine-free cola. That's your control group. All students then measured their pulse rates again. The table displays the change in pulse rates for the students in both groups. So here is our data here. Notice they give us the raw data and they give us the mean change, but we can't really do much unless we have the standard deviation as well if we're going to be using it by hand. So at the end of the day, you still got to, put that data into your calculator and get that information, the standard deviation, so that way you can construct your interval here. All right, the questions are construct and interpret a 95% confidence interval. I mean, right off the bat, it says interval, so we know we're going to do an interval here for the difference in the true mean pulse rate for subjects like these who drink caffeine versus drink no caffeine. And then there's a second part of the interval. A lot of times these intervals will suggest, what does this say about a certain value? So in this case here, what does the interval in part A suggest about whether caffeine increases the average pulse rate of subjects like these? And, when it comes down to something like that, we're thinking, well, if there isn't significant evidence that there's an increase, then we would see our interval probably be not include 0, if that makes sense. So let's look at this first part here. Construct and interpret a 95% confidence interval and the true mean pulse rates for subjects like these who drink caffeine versus who drink no caffeine. Well, we want to state what we're doing. We want to name the interval. So what is this interval? Well, it's a 2-sample t interval for mu1 minus mu2. How do we know it's 2 samples? Because these are random assigned 2 groups. It's not one person doing both treatments at different times and measuring the change. These are 2 groups from the same population, which is the class of 20. So I'm just going to name the interval, state the confidence level. And then what else do? We have to define mu1 and mu2. So what are they? Well, mu1 would be the true mean change in pulse rates for students like these after drinking the cola with caffeine, while mu2 is the change in pulse rates for students like these after drinking the caffeine-free cola. So make sure you define which one's which, because if you're going to input that data in the calculator, we have to go in the right order. And the calculator is going to do mu1 minus mu2. So if you want the first one to be caffeine and the second one to be no caffeine, then you have to make sure that you define it that way, set it up that way. All right, your plan part. You got to name your conditions. So your conditions are random, 10%. Do we need the 10% here? And approximately normal. Why don't you pause it and try that part? All right, for our random, volunteers were randomly assigned to drink either cola with caffeine or caffeine-free cola. We were told that in the problem. You can go back to the stem of the problem and see that. 20 students in this class volunteered. All the students measured their initial pulse rates. Mr. Wilcox randomly assigned the students into 2 groups of 10. So it's right there in the problem. And that's your random condition. And this is a controlled comparative experiment. We are taking volunteers. This is not a selection from a larger population, so we don't do the 10% condition here. Now, as far as the sample sizes go, they are small. We don't know if this population is normal, and we're not told that. And we're not dealing with 30 or more, so we can't say the sampling distribution is going to be normal because of the central limit theorem. So we do have to plot the data. Now, let me walk you through what I have over here in these steps here. You first want to make sure your data is entered in your stat menu. So make sure that you go to stat edit and you put L1 and L2. Now I keep L1 mu1 and I keep L2 mu2, or the sample for mu1 and mu2, just to keep things, you know, simple. And then I want to make sure that my plots are accurately reflective of something that doesn't have super strong skewness or outliers. So I'm going to go into my second y equals, and I'm going to turn on both plot 1 and plot 2. And I want to look at a box plot. All right, box plot is probably the easiest one to look at. It'll show if there are outliers or skewness. And I'm going to turn on plot 2 as well. So we're going to put those together. So make sure you're doing that, both turning them both on so you can look at both of them on a graph. We're going to hit zoom 9. And you can see that data entered in. Oops, let me fix out what I have in my data. Something's wrong. Hold on a second. Well, I know exactly what I did, so don't make the same mistake I did. Under plot 2, I kept L1 as L1. Obviously, that gave me the same graph. That wasn't very useful. So we want to make sure we change that to L2, so we're pulling that plot from the second list. Duh. All right, so now let's do zoom 9. And there's a sketch of your plots. Of course, you don't need to draw the axes. Those are not really super helpful. So when you're going to jot that down, what I do on this problem is first, I comment about the plots. You know, there are no strong skewness, there's no outliers. I sketch the plots. Now you can also draw a dot plot if you wish. Dot plots are not going to involve having to use your stat menu or your calculator's plot menu. You can just draw your axes, label them, put the dots on there, and be good with it. So if you want to use a dot plot, if it's easy to use, like if they're whole numbers or integers, go for it. I usually just stick with the box plots in general, just to make things easier. But sketch those plots and make that commentary on those plots. That's your do part, or your plan part. Calculator time. Once you get to the do part, I would shy away from doing anything with your formulas unless it's a multiple choice question and it requires it. So with this part here, we're just going to use our calculator. So we're going to make sure we run the interval. So this is going to be a 2 sample t interval. And because we have the data here, that's going to be option 0, 2 samp t int. And we're going to go to data. And the data will pull from L1 and L2 as a default. So just make sure you set your confidence level to whatever it is, in this case, 95%. Make sure you select no for pooled and calculate. We should get the following menu. We're going to write all that down because the only thing we're given is the mean change. We weren't given the sample standard deviations and the sample size, although we know it's 10. So we have to jot all that information down with the right notation. So what would that look like on here? Something like this. Just you can state that you use technology to get that information. It's not going to hurt anything. Jot that interval down, the degree of freedom. the X bar one. Now I put all the one samples in one and the other sample in the other. It's kind of, separating it like that. If you want to do that, you can, but just make sure all that notation is there correctly. And then finally, our conclusion. We got to interpret that interval. So we are 95% confident that what? That the interval between negative 1.302 and 3.7017 beats per minute captures the true difference in the true mean change in pulse rates for these students, like these, after drinking cola with caffeine versus without caffeine. Oops, let's fix that typo. And so always include context in this part, okay? We are 95% confident that the intervals between this and this isn't going to get you full credit. Throw that context in there and make sure you use the units for these because we're talking about quantitative data. So beats per minute would be your units. Now there's a second part of this question, which you couldn't answer unless you answered the conclude part or the do part, which is, what does the interval in part A suggest about whether caffeine increases the average pulse rate of subjects like these? And justify your answer. Well, the interval is between negative 1.302 and positive 3.07017. What number is in that interval that might suggest we don't have significant evidence to conclude that there's an increase? You guessed it, the interval contains 0. So the interval in part A does not suggest that caffeine increases the average pulse rates of subjects like these. And because the interval does contain 0, it is plausible that the true mean change in pulse rates for all students like these may equal 0, indicating no difference. So that's how you work that problem out. Now, this isn't on your handout here, but let's just think about this problem. You might look at this question and think, well, these guys really should be paired data because somebody might be affected differently by caffeine individually than just a randomly assigned groups of people. So could we conduct that in a way where we'd use a one sample difference in paired data? And it can be done. I want you to look at this problem here. I'm not going to work it out. I just kind of pulled it from the textbook here. Read through that problem and you can see how it's set up as a paired data. If you want to pause that video here, you can read through it on your own. It says researchers designed an experiment to study the effects of caffeine withdrawal. They recruited 11 volunteers who were diagnosed as being caffeine dependent to serve each subject. Each subject was barred from coffee, colas, and other substances with caffeine for the duration of the experiment. During one 2-day period, subjects took capsules containing their normal caffeine intake. During another 2-day period, they took placebo capsules. So we're up in our caffeine game here. We're doing more than just cola. We're talking about legit pills with caffeine. So yeah, we might see some difference here. But in this case here, we're trying to measure depression, not pulse rate. So it's a different problem. But regardless, notice that they did this as a 2-day period. So for one day, let's see, during one 2-day period, subjects took capsules containing their normal caffeine intake. And then during another 2-day period, they took placebo capsules. The order in which the subject took caffeine and the placebo was randomized. So each person was randomized. The order of each person was randomized. And at the end of the 2-day period, a test for depression was given to all 11 subjects. And they didn't say, did it say how far apart those 2-day periods were? Hopefully far enough apart where the effects have worn off from the caffeine. Regardless here, this would be paired data because, each individual subject, right, has its own kind of blocking, right? And we're talking about the difference between these two. So at the end of the day, when we're doing that data here, we want to get the difference of these and plot that and use that for our interval or test. In this case here, do the data provide convincing evidence at the 5% level that the caffeine withdrawal increases depression score on average for subjects like the one in the experiment? Well, this is going to be a test, right? Because we're talking about an alpha. So I just kind of went ahead and put the solutions up here so you could see that this would be a paired data. So it's equal to 0 for your null, greater than 0 for your alternative. And we use the mu diff notation for that because we're trying to get the individual differences first. And then at the end of the day, use that one set of data to run a test. And you can see it worked out here. I'm not going to walk you through everything, but understand the difference between 2 sample versus 1 sample. All right, let's look at the other check your understanding from your handout. Pause the video if you want to read through it on your own. Does increasing the amount of calcium in our diet reduce blood pressure? Examination of a large sample of people revealed a relationship between calcium intake and blood pressure. Such observational studies do not establish causation. Researchers therefore designed a randomized comparative experiment. The subjects were 21 healthy men who volunteered to take part in the experiment. They were randomly assigned to 2 groups. 10 of the men received a calcium supplement for 12 weeks, while the control group of 11 men received a placebo pill that looked identical. The experiment was double-blind. Remember what that means? It means that both the experimenters and the subjects do not know which pill is being administered to an individual subject. And that is important because we don't want to incorporate any bias in that. Hey, you're going to get the placebo. Hey, you're going to get the calcium. The response variable is the decrease in systolic top number. The systolic blood pressure, which is the top number here, for the subject after 12 weeks in millimeters of mercury, which whatever that is. An increase appears as a negative number. Here are the data. So here are your group 1 for calcium. Look at the numbers. You see a little bit more negative numbers on the group 1 than you see on the group 2. That might indicate for us that there might be some evidence that there is an increase or a decrease in systolic blood pressure, because an increase is a negative number. So let's look at the data here and let's see what the question states. Do these data provide convincing evidence? Evidence. Interval? Test? Which one is that? Convincing evidence that a calcium supplement reduces blood pressure more than a placebo on average for subjects like the ones in the study. And then at the end, interpret the p-value you got in part A in the context of this experiment. Well, I know that a p-value is from a test, so that kind of tells me I'm going to use a test, even though convincing evidence right there, that is also your clue. That's going to be a test right there. Well, let's look at the question. So if it's a test, what are we going to do first? We're going to name the test, right? What is this procedure called? Well, how many samples are we dealing with? 2. The 2 sample t-test for mu C minus mu P. Now I use C and P, calcium and placebo. You can use 1 and 2, doesn't matter. Whatever notation you want, be consistent with it. If you're going to use 1 and 2, then keep it as 1 and 2. If you're going to use C and P, then keep it as C and P. I don't care, but make sure that you don't switch it up in the middle. All right, so what is this procedure called? It's a 2 sample t-test for mu1 minus mu2. Now, what are our parameters? Well, mu C is the true mean decrease in systolic blood pressure for men like those in the study who take the calcium, C for calcium, and then P is the mean decrease in systolic blood pressure for men like those in the study who take placebo. Define your parameters. Are we given an alpha level? Not in this case. So we do want to make sure that we state one. That's more important here because we're not given one. So make sure you state your alpha level. But let's go ahead and do our hypotheses first, because that's kind of tricky here. Now, in this question here, we know that the null is going to be they're equal to each other. Okay, that we're kind of always going to have that for our null for 2 sample, but for the alternative, we got to be careful with what we're looking for. Now, if you're stuck on, well, is it greater than or less than? I just want you to think about the numbers first. I'm going to pause the video and enter this data in. All right, now I entered the data in L1 and L2, and I know I haven't got to the plan part yet or anything like that, but I do notice that on average, it seems like these tend to be a little bit higher than these. So without even throwing in context of the problem, I'm not going to really get significant results unless I set my inequality symbol to be greater than, in this case here. Now, if I look at the plots, okay, if you just want to go on the plots, second y equals, I already have my plots turned on, but you can turn your plots on in your stat plot menu and make sure you pull from L1 and L2. And if you look at the 2 plots, you're going to see that the blue one, which in this case is the calcium group, it is higher on average than the red one, which is my placebo. So I know that I should probably make my alternative to be greater than, okay? At the end of the day, what does that mean? Well, I just went back to the problem here and I looked at where it said increase appears as a negative number, okay? Increase, but we're looking for a decrease. So a decrease being positive, increase is negative. I want to show that calcium increases over the placebo. So yeah, it's going to be greater than that wording is rough, but that's how that works here. Okay. Now we've defined our parameter, we've stated our hypotheses. Alpha level is going to be 5%. Let's go through and do the plan part. Our conditions. Of course, they're randomly assigned to different treatments, calcium or placebo. It is 2 random samples or random assignment groups, treatment groups. No 10% condition again, it's an experiment, so we don't have to worry about sampling from a larger population. Let's graph that data. We got L1 and L2, and again, you can get the graph of the data and kind of see both box plots, or you can make a dot plot again. These are easy numbers to work with a dot plot, so don't be afraid to do that. And then make sure you comment on their skewness and lack of outliers. All right, there can be skewed, they just can't be super strongly skewed. And in our case here, we're not trying to get you here. I'm not trying to say, hey, I got you. I made you do a test when you shouldn't have. Just comment on the skewness and the lack of outliers. And as long as the skewness isn't super heavy and your outliers are non-existent, you can go ahead and do it. Okay. Now, as far as the do part goes, go to your calculator and get that data in. Now, I have the data in L1 and L2. So this is going to be stat test 2 SAMP t-test, option number 4. And because our data is entered in L1 and L2, make sure that we, in this case, do the greater than, because we are testing to see if this is bigger than that. Keep it at no for pooled and go down to calculate. And there is your test statistic, 1.6, your p-value of about 6.44%, degree of freedom 15.59, and all the other summary statistics. If you scroll down, you can get the samples. Now, I'm calling 1 the C and 2 the P. So if you're going to write down 1 and 2, then you're going to have to go back to your state part and make sure you define mu1 as calcium and mu2 as placebo. All right, when you're running that information here, again, just like I said, X1 and X2, that should be a bar there. Hold on a second. So X bar 1 and X bar 2, if you're going to write those, then make sure you define your parameters as mu1 and mu2. And write down all your valuable statistics there that come from your data. And let's make our conclusion. All right, our conclusion, of course, pretty large p-value. We set our alpha level at 5%. Our p-value is at about 6.44%. So you know what that's going to look like. That's right. P-value is going to be greater than our alpha. So we're going to fail to reject. Since our p-value is of 0.0644 is greater than alpha, we fail to reject. We do not have convincing evidence in this case, statistically significant, that it's not statistically significant evidence that the true mean decrease in systolic blood pressure is higher for men like these in the study who take calcium than for men like those who take a placebo. And next part, interpret the p-value. Well, remember a p-value, the generic definition for p-value, this is from a template sheet I shared with you, is assuming the null is true. If the null is true, the probability of obtaining results at least as extreme as the sample that we saw is whatever your p-value is, okay? So that p-value is the number in the blank there. So in this problem here, try to get this interpretation. Pause the video before I go over it. Here we go. Assuming that the null is true, that there is no difference between the calcium blood pressure decrease and the placebo blood pressure decrease. The probability of getting a difference, calcium minus placebo, in mean blood pressure reduction for the two groups as much as or greater than what we observed is 0.0644. Assuming that there is no difference, the likelihood that we got a sample as great or more than what we as extreme or more extreme than what we observed is about 6.44%. That's the interpretation of the p-value in this context. Well, I hope this video was helpful for you, and you can go ahead and do your day 4 assignment and let me know if you have any questions. Thank you. Bye.